We're going to take a look at the series, the summation from 2 to infinity of 1 divided by n squared minus 1. We want to know if this series converges or diverges, and if it converges, we want to know what does it converge to. So first thing we're going to do, because the denominator is n squared minus 1, we can factor the denominator and express the series in this form as a product of two linear terms in the denominator, n minus 1 times n plus 1. And now let's write out the first few terms. When n is equal to 2, this is 1 divided by 1 times 3 plus 1 divided by 2 times 4 plus 1 divided by 3 times 5 plus 1 divided by 4 times 6 and so on. So this is equal to 1/3 plus 1 over 8 plus 1/15 plus 1 over 24 and so on. Now this is not a geometric series, because if we take a ratio of a term divided by its predecessor, so 1 over 8 divided by 1 over 3 is 3/8. 1/15 divided by 1/8 is 8 over 15. And 1/24 over 1/15 is 15 divided by 24, which is 5 over 8. So if this was a geometric series, all these ratios would be the same, but since they're not, this is not a geometric series and we cannot solve it that way. The next thing we can do is test for divergence to see if we can detect that this series diverges. So we take limit as n goes to infinity of the nth term of our series, which is 1 over n squared minus 1. If this limit is not 0, the series will diverge and will be done, but this limit is 0. And the test for divergence is inconclusive, which means we have to try something else. So what do we have to do? We have to go back to the definition of a series. So suppose we have a series. It doesn't matter that our series starts at 2. Suppose series starts at 1 of an. This is a1 plus a2 plus a3 and plus a4 and so on. So from this sequence of an's, we define a series by adding up all the terms. We also can create a new sequence, which we call S sub n. I use capital N here instead of a small n. This is called the sequence of nth partial sums, where Sn is equal to the summation. Little n goes from 1 to big N of an, and this is just a1 plus a2 plus a3 all the way up to an. So it's the sum of the first n terms of our series. And so the series itself is defined, the summation from 1 to infinity an is defined as the limit capital N goes to infinity of the sequence of the nth partial sum, so Sn. If this limit exists and it is a finite number, the series converges to that number. If the limit doesn't exist, we say the series diverges. But the problem is, in practice, it's very difficult to express Sn in a way that we can evaluate the limit. So theoretically it's great, but in practice it's not very good. But however, for this example, we can express Sn in a way that the limit can be computed. So we return to our series and we look at it in this form. N goes from 2 to infinity, 1 divided by n minus 1 times n plus 1. You may recognize this. We work with something similar when we work with integration by method of partial fractions. So we'll take this rational function that is 1 divided by a product of two linear polynomials, write it as a over the first plus b over the second, and multiply both sides by the denominator from the left, and we have 1 equals a times n plus 1 plus b times n minus 1. Now let's plug in n equals 1. That gives us 1 equals to 2a. So a must be 1/2. And we plug in n equals to minus 1. That's 1 equals minus 2b. So b must be minus 1/2. So this series can be expressed as the summation from 2 to infinity 1a, which is 1/2, so this is 1/2, and then we have n minus 1 there with the 2 in the denominator, minus 1 divided by 2 times n plus 1. And it is in this form that we can find a formula for Sn. Now let's pick a number. Let's before we actually find the formula, let's pick a number. Let's pick n to be big N to be 8. We want to compute S8. So S8 is computed like this. We first plug in 2. It's wherever we start. For n, we get 1/2 minus 1 divided by 6, plus when n is equal to 3, that's 1/4 minus 1 over 8. When n is 4, that's going to give us 1/6 minus 1/10. When n is 5, that's going to be 1 over 8 minus 1/12. When n is equal to 6, it is 1 over 10 minus 1 over 14. When n is 7, that's 1 divided by 12 minus 1 over 16. And finally, when n is 8, that will be 1/14, and then minus 1 over 18. Well, look what happens. This is an example. What we have here is a telescoping series because most of the terms in Sn will cancel. The middle terms will cancel, which will leave us just a few terms. Here's minus 1/6. It cancels with positive 1/6. Here's minus 1/8. It cancels with positive 1/8. Minus 1 over 10 and 1 over 10. Minus 1 over 12 and 1 over 12. Minus 1/14 cancels with 1/14. Now what is left is the 1/2 plus the 1/4 minus 1/16 minus 1/18. Now what we don't want to do is simplify too much because we want to have an idea what this is in terms of the last number, which in this case is 8, and generalize it to Sn for any n. So the 1/2 and the 1/4 we can simplify. That is 3 over 4. And then minus 1/16, that's 1 divided by 2 times the last number, which is 8. And 1/18 can be written as 1 divided by 2 times the last number plus 1. So this is a formula for S8. This is what S8 is going to be. We can generalize this to Sn by, we still have the 3 over 4, but then minus 1 divided by 2 times the last number, which is n, minus 1 divided by 2 times the last number n plus 1. And let's just go through the computation briefly to make sure that that is in fact the case. So Sn will be, first we plug in 2 for n, that will be 1/2 minus 1/6 plus 1 over 4 minus 1 over 8 plus 1/6 minus 1/10 plus 1 over 8 minus 1 over 12 plus, and so on, until, let's say, we get to the following 4 terms. N equals n minus 3, n equals to n minus 2, little n equals n minus 1, and finally little n equals to big N. So we want to add those terms and see what happens. For n minus 3, subtracting 1, that's n minus 4 times 2 would be 1 divided by 2n minus 8, and then adding 1 would be n minus 2, so minus 1 divided by 2n minus 4. Plus, when little n is n minus 2, subtracting 1, that's n minus 3, so 1 divided by 2n minus 6, minus, and then adding 1 would be n minus 1, so this is 1 over 2n minus 2. Plus, when little n is n minus 1, subtracting 1 would be n minus 2, so this is 1 divided by 2n minus 4 minus 1 over 2n. And finally, the last one, when little n is big N, that would be 1 divided by 2n minus 2 minus 1 divided by 2 times n plus 1 or 2n plus 2. So once again, minus 1/6 and 1/6, minus 1/8 and 1/8, all the terms will cancel except this 1/2, the 1/4, and over here we have 1 over 2n minus 4 cancels with 1 over positive with 2n minus 4, and then here is 2n minus 2 will cancel with 1 over 2n minus 2. 2n minus 6 will cancel with the term before that, so is 1 over 2n minus 8. And what's left are these two terms, 1 over 2n and 1 over 2n plus 1, just like we predicted for when we computed S8. So the formula for Sn is equal to 1/2 plus 1/4 minus 1 over 2n minus 1 over 2 times n plus 1, which is 3 over 4 minus 1 over 2n minus 1 over 2n plus 1. Now we can combine the 1 over 2n and 1 over 2n plus 1, but there's no need to do that. And we finally can solve this problem. Here's how the last step works. We had a series from 2 to infinity, 1 over n squared minus 1. We rewrote it as the series from 2 to infinity, 1 over n minus 1 times n plus 1. After partial fraction decomposition, this is the summation from 2 to infinity of 1 divided by 2 times n minus 1 minus 1 divided by 2 times n plus 1. And this is equal to the limit as big N goes to infinity of the sequence of nth partial sum Sn. And we have a formula for that. So this is limit big N goes to infinity of 3 over 4 minus 1 over 2n minus 1 divided by 2 times n plus 1. And so both of these that have the 2n and 2n plus 1 in the denominator, those go to 0, and the final answer is 3 over 4. So we can now make the final summary that the series summation from 2 to infinity of 1 divided by n squared minus 1 converges to 3/4. For more videos, visit www.mathprepvideos.com.